All right. So as we're going through stuff, this graph can be hard to interpret. And I'll tell you, in a physics class, this is a hard idea to get through. Even in a calculus class where this stuff really starts to hit, conceptually it can be difficult to look at. Now, I see that, am I getting further away or closer to where I started, first and foremost? I'm getting further, right? Whatever this distance is, and I'm just going to make up numbers. You don't have to add these to yours. I think it was that orange, though. If I went, like, let's say, let's do 3 meters. I want to check this out. If I start here, and you were to look at how quickly my position is changing over time on that first interval, from T1 to T2, if you were to look, it starts going really slow initially, right? So it's like I'm doing this for the first part, and then I keep speeding up until I get to T1. When you see this happening, this is called concave up. Don't care if we use that language or not. But here, over this amount of time, it's just a little tiny change, right? If we look over the same amount of time here, is this a larger change in position? And if you have a larger change in position over the same amount of time, what must have happened? You have to be going faster and faster. So, same thing happens over this next interval. Even from here to here, that's a larger change again. This entire time on that first interval, what are we doing? Speeding up is an okay way to say it. Is there a different way that you guys know to say it? Good. Speed up or accelerate. Now, once we get there, and it's hard to model, let me see, I tried for a few minutes. I had to adjust the settings to play with it, and even with doing so, there's still a little bit of error, sorry. Okay, so let's check on this one, T1 to T2. There's some change in position, but if I go this amount of time and go that much up, is it the same amount of time and that much up again? So I'm going the same distance in the same amount of time, which says, what is going on? Am I speeding up anymore? Consistent, or what's a speed that doesn't change? There might be another word. Instead of consistent, constant. Constant speed. Okay, this last little piece. I'm going to erase those other steps that we drew in there because I don't like them. This last little piece. If I'm going here, I'm going to try to emulate this as best I can. I can't really speed up super well, but check it out. We don't need super high velocities. Here I am going really slow to start. I start speeding up, and then I get to my max speed. I slow down a little bit, and I walk consistently. And then I'm at T2 right now. What do? I stop because what's happening with my position? It doesn't change. And the only way that that can happen is if I stop. Now, hypothetically, and you guys don't have to add this to yours. I just want to be able to think about it. Let's say one more trip was added onto this, and I did that. So now here I am, slowly starting, speeding up a little bit, then slowing down and walking consistently, and then I stop at a constant speed. I like your word consistent, though, apparently. What's that last little trip, T3 to T4, going to tell me I do?
You'll run backwards.
So do I have to run? Is that at a constant speed, or is that speeding up, or what's happening? Constant speed back to where? To zero, wherever I started, right? And I can see that these graphs, they take some practice, but I think and I hope you guys can see that those are what we're looking at. So when I tried to model this, we'll see I didn't do like the best job ever, but just kidding, that's unreadable. All I did was I played with the monitor, these little Vernier things, and I just started here, I set the time larger, then I started moving my hand really slow and sped it up, and then I tried to go away at a constant speed, and then I stopped. And it wasn't exactly this shape because it's really hard to model it exactly, but pretty close was the way. It's exactly what I just did walking through here. Easier to move the monitor than it is to move stuff in front of it, just so you guys are aware. Okay, so this one we'll just say stop. Now, going through these, there are some problems that I want us to be able to work through, but we have a couple definitions that I want to hit first, and then realistically, today is going to be mostly a work day of getting practice with it. We can do them together. We can do them individually with your teams. Whatever you guys want to do, I'm fine with. But let's go ahead and jump in. We have a couple definitions, and then we'll do a problem or two together, and then give you some time to work and get practice with these ideas. So, two big words that you're going to see all the time. And I'm just going to throw it right in. And what color are we using today, Rafa? Go what? Blue, all right. Nice, lovely light blue. So, couple definitions, realistically one definition. One of the things that we're going to see, and totally, just so you know, you might have started seeing this already. If I write the word instantaneous, it is very possible that you have never seen this word in your life. Instantaneous. Anybody ever seen that word exactly like that? Now check out our powers of deduction though, because I have a feeling that more than one person here has a good idea of what this means. Instantaneous means what, would you say? At this instant. Now, there's weird ideas that hopefully you guys remember. A line goes on forever, right? Infinitely many points. How big is a point? So on your page it shows up as a dot, right? But like if I wanted to identify a point, and don't draw this, just me talking. If I wanted to identify a point, say 1, 1. Does that do a good job of it? If that's 1 and 1. It does okay, right? Now, how about this? Does this do a good job of it? Okay? The smaller I get, the closer I actually am, right? Because otherwise I'm overlapping 1.000001 and so forth and so on. From geometry, points, if you don't recall, are infinitely small, which makes it a weird idea. And this is where the calculus kicks in, because instantaneous means at a single location in time, not a tiny increment, but a single location. So when we talk about instantaneous, we're going to see this show up over and over. We're going to talk about instantaneous position. And I don't think we have to be real crazy with it. We're just going to say the position of an object. And I'm going to throw in a wonky math word that I think, or hope at least, clears it up. The position of an object at a single, and then here's a weird idea. We're going to say non-finite because you can't even say it's a number. Infinite means without end, right? Finite just means it ends. You can't think about time and a single instant in time as being a number because it, like, you can say it's this many seconds after, but there's really no size to it. It's non-finite. It's not a number. It's infinitely small. Okay. The point in time. Easy. Now, the nice thing is that most of the time, if I ask you guys for, oh, at this time, what's the position? It's implied, and we all work with the understanding that we're just looking for an instantaneous position every single time. Unless you're looking for a change in it, it's always just going to be position, but this is what it's really referring to. Okay. Now, when we work through, and I'm just going to make a comment here. Oftentimes we deal with the motion of not just one thing, but multiple things at the same time. So when you're doing that sort of system and you're setting it up, make sure that you include all the information needed to get your context. And there's some really misleading things that might happen. So I'm going to have us do a hard problem together, and then I'm going to give you guys some easier problems to work amongst yourselves. So let's check it out. We are going to look, I don't want to write a whole paragraph. I want you guys to open up your books to page 43. If you don't happen to have your book, I will put this up on the board as well. But I don't want to have to write a paragraph for it. So in our notes when we're dealing with these sorts of things, here's my suggestion, but I'm open to changing if needed. First of all, I'm going to move over here so I can get a bigger graph if we need it. For this example, if we don't want to have to write everything down, I'm just going to say page 43. So it says it's a challenge. I don't know that I'd really call it a challenge. But we'll just say it's challenge on page 43 of your text. If you'd like to write a whole paragraph of stuff, you're welcome to. I'm never going to require it. So let me open this up. I will copy and paste, preferably not upside down, this problem. But I'll have you guys also make sure you read it and stuff because we're going to be referencing it. Okay, shadow, stop it. All right, we're just going to deal with the shadow. Zoom out just a skosh. Do you guys ever like copy and paste stuff, like pictures and all that, when you're working on documents and whatever? Probably. How do you do it? Like, do you just print screen and then go in and save it? Okay, so side thing, if every single one of your computers that you'll ever have, if it's not your phone, you have this thing called snipping tool that I use this constantly, and it just allows you to select a little portion of whatever's on your screen. All right. There it is. So we have 3 people, Natana, Olivia, and Phil, and they're enjoying all their exercise along a river path. Natana bicycles at a consistent or constant 40.25 kilometers per hour. Olivia's running at 16 kilometers per hour south, it says, and Phil walks quickly at 6.5 kilometers per hour. Now, we have some other information going on here, but we're going to do 3 different things. First thing we're going to do is on the same plane. We want to compare this information that's going to help us make sense of it. What is the challenge part of this is how do we set it up to actually make sense? So, I'll have you guys read through this, and then my question for you is we're going to do part 1 first. We want to draw a position and time graph. So my challenge for you initially is I'm going to draw a scale here. I want you to pick me, or I'm going to draw a coordinate system. I want you to pick me the scale and the axes that we need to assign. So read through this. It's a challenge. It's worded super wonky. What I would suggest, and you guys have it written in front of you, but something that's always helpful is what do we know about this problem already? So I'll give you guys a second. We have all the known information. If you want to record it, you can. I will, but I'm going to start with just this. And there's our problem again. Your job is between you and your team to figure out what should the axes be and what are the scales that we should possibly use. However, we spoke before about variables and stuff. Which of those variables do you think is going to be the independent axis? Especially if we're making a position time graph. So I'm going to say time, right? Now, here's where it gets weird. If I label this time, and I'm fine with that, I'm even okay with hours, but we have something strange going on. Nat, Phil, and Olivia start at the same time or different times? Different. So, who starts first? Olivia and Phil, they start walking or running south, right? From where? How high up? 20 kilometers. So if we have time and position here, it would probably be a decent idea to let's fix our scale. The position is kilometers, and notice I haven't added a time yet. You guys are right that it's going to be hours, but we're going to shift this a little bit. Because 11:30 is a.m., which typically if I said it's 0 hour right now, what time of the day is it? 0 is 12 a.m., like midnight. So we can either have this be 0 and then have to jump all the way out to 11 and a half hours away and then deal with it. Or, Toli, what did you do? This is 11:30. Now, if that's 11:30, here's kind of the easiest way to go through this. If you write that, that's fine. I would call this T naught or TI, either one. And then based on our scale, we're going to pick time and we're going hours. But it's specifically hours since when? What time do we start? 11:30. So what I would suggest to make this a little bit nicer to deal with, let's just call this whole, it is time, but let's say hours since 11:30. And then what that allows is you don't have to get rid of it, but then all of a sudden that doesn't really mean anything. Because 0 hours after 11:30 is 0 still, right? Okay. That felt like a big statement. Do y'all understand that part? I just don't, like, we could do it the other way. I just don't want to have to shift the whole graph. Now, for this, I want to do a little bit of thinking. I know I have to go 20 kilometers. So if I choose these, and I should have gone a little bit higher, my scale works out pretty nicely. So that's 5 kilometers, 15 kilometers, and 20 kilometers, right? And I went all the way up to the top of my scale. Equally spaced, doesn't have to be like perfect because we're not just going to blindly trust our graphs anyway. But I think that covers everything that I need, all the way up to 20 kilometers. Time stuff, we could start thinking about immediately. And I would suggest it because right now, if I don't say anything else, this first increment of time is how long? That's pretty natural, but let's think this out real quick. Who's riding the bike? Is it Nat? And how fast is she going? So how long will it take her to go like all the way north? If she's going 40 kilometers per hour and she has to go 20 kilometers, how long is it going to take her? So that means that Natalia's stuff would just be this simple little part of this graph, and it kind of condenses it, right? And we'll deal with that here in a second. Instead of making small ticks, I think we should do like 0.25 of an hour and 0.5 of an hour. And we could go more than this or less than this, but I think that based on that, knowing that, hey, we really only need a full hour to see Nat's whole trip, we're going to save ourselves a little bit of time here. Okay, so 0.75 and 1 hour. Okay, so we're trying to draw their position versus time graphs. In your opinion, with your groups, and actually talk this out, don't just sit there quietly for a minute, what makes this problem seem so hard? And maybe it doesn't seem crazy hard right this second, but there's one thing that I look at this problem, and the math part's not hard, the physics part's not hard, but something about it is really convoluted. I agree with you, Fern. I had to read this thing like 3 times because the wonky order that it gives me. Now, that will happen just because the order that data shows up in is how you're going to write it down initially. And they're trying to make sure that you can keep track of stuff. Now, we haven't talked at all about velocity explicitly anyway. We haven't even really talked about speed in here. Do you guys recall what speed is? Like, you know what speed is conceptually. You know the speed limit outside. What is the speed limit on this road? 30 what? For how many hours? So 30 miles per 1 hour, right? That's our speed. Miles is a measure of what? Distance. And hours are a measure of time. So if we need it, I'm going to make a quick little comment here. Just a tool that I think you guys knew, but I want to reemphasize that. The speed of an object is just distance over time. Now, we will tie this to the idea of velocity in the coming days because there is a difference between velocity and speed. It's subtle, but there is a difference nonetheless. Now, once we have this, let's just start graphing, and I'm just going to use 3 different colors. You guys may not have that ability, but it's going to help make stuff clearer. I'm just going to say Natalie, Natalia, what's her name? Natana. I'm just going to call her Nat. Let's say Nat is green. What color is Olivia? I lied. I already picked it. She's yellow. And apparently I don't believe in capitalizing names, so we're just going to stick with it. And lastly, we have Phil, right? Okay. We're going to deal with those 3. I don't care whose graph we draw first. Thoughts? All right, we're going to draw Phil first. Phil starts where? So we have 2 situations here, and if you want the context added, we have a waterfall and a dock, right? Is that correct? Waterfall is like here. And we have a dock up here. Okay, does Phil start at the waterfall or the dock? Starts at the dock, which is how many kilometers north of the waterfall? All right, so I start there, and then here's where we have to start making connections. Here's where Phil starts, 20 kilometers north. Now, I need to be able to get at least 2 points. Luckily for us, they're all working at constant speeds, or constant velocities. They're not varying at all. I need another point to draw Phil's line now. How fast does Phil walk? 6.5 kilometers per hour, which means as I'm looking at this, if I were to eyeball, and I'm cool with it because we're not just going to blindly trust our graphs, if I were to say 6.5 kilometers, that would put me about here. Are you guys cool with that? Because I went 6.5 would be, let's see, 5 would be 15, and then a little bit more. And that took how long to get there? An hour. So I'm going to put that point here. Now, is that a perfect point? No, but I can see that he went 6.5 kilometers south, or downward on our graph, over the time span of 1 hour. I now have 2 points. There's Phil. Look at him. He's enjoying his life. Okay. I'm going to give you guys a minute. There are straight edges in your desk if you need them, but we're not going to just blindly trust our graphs. I want you to give me the graph of Olivia and Phil. If anybody decides you want to be nice and bright and colorful, there's a box of colored pencils on the back counter that you are welcome to use if you'd like. They're actually going to be on the back desk here in case somebody wants them. Yes. Should we try the Bluetooth situation so I can just put it on people's desks? So read the problem for me real quick and tell me where Phil starts. You might have to read it a couple times because it's wonky. Okay, that's cool. Feeling okay, or are you kind of looking at it like not quite sure? Okay, you're fine. Yeah. Like it tells us, right? Yeah. It's so oddly worded. Cool. If you're not using colored pencils and stuff, make sure you label the lines, because we're going to have 3 lines on this thing, and we don't want to get them mixed up. Looking at this, inevitably somebody wrote this and had no idea how I got those points, I would imagine. It happens. Don't be scared to ask questions. Everybody will have them. Let's do Olivia next. And I recorded stuff here. Why did I write Olivia and Phil are negative? They're going south, right? We're just going to call that negative. So Olivia, over the course of 1 hour, if she starts at 20 kilometers north, 1 hour, she'll go how far south? 16. So I'm going to eyeball it, and I actually not on mine because I can do it. Do you guys agree that after 1 hour, she is going to be 4 meters north of the waterfall? And that was at that time, right? Okay, I know she started here and she's walking this way. Okay. We have their stuff done. Now, I might have intentionally tried to mislead you guys a little bit, but for a meaningful reason, I promise. Nat's is weird. Why? She starts later. What time did Nat start biking? At noon, which is how many hours since 11:30? 0.5. So Nat doesn't even show up in this picture until we get here. At 0, or right at noon, the instant before she leaves, instantaneous position, she's just 0 meters north. Now, here's the issue. I have to go all the way up to 40.25 and an hour and a half if we want to do this. If only we knew that fractions could be equivalent and simplified. Instead of 40.25 kilometers in 1 full hour, based on the scale that I've kind of pigeonholed us into, I can't go a full hour. What should I go instead? If she goes 40.25 kilometers in 1 full hour, how far does she go in half an hour? 20.125 is what it winds up being. So if I go here, 20.125 is just a hair above 20. There is Nat. Now, for labeling stuff, it is entirely up to you. I have the colors coded here, which makes it nice, but you don't have to use colors. So I'll just make the time to, 1, capitalize, but also knock them out. Just fun fact, or not very fun fact, but a random fact. Olivia is easily the most common baby girl name in the U.S., like in 35 states or more. Olivia is going to be the name that shows up for the next however many years. Guess on the most common boy's name for 2023? Jack is only Mississippi.
Liam.
It's Liam. Interesting. Do you know a bunch of baby Liams? What made you guess Liam? Cool. Awesome. All right. So here these guys are. Now we're about to get real mathy, so stretch the math muscles. You can put on an imaginary math hat if you want. Okay. That's part 1. Cool. Baller. This thing is super convoluted and gross to look at when you read through it. Does it feel better now where you're just thinking to yourself, thank goodness Holloway helped because that sucked? I feel good, thumbs up. I feel bad, thumbs down. Somewhere in between. Okay. So, what's the next part of this question? Yeah, go ahead, read it.
At what time will three exercise enthusiasts be located within the smallest distance interval from each
Everybody talks like that, right? At what point in time will these three exercise enthusiasts? Such a weird wording. Okay, when will they be closest together is a question. That's it. At what time? Okay, that is possibly a tough question. Talk with your neighbors. Find me the point where the distance between all three of them is the smallest in your mind. You'll have a good eyeball guess based on our graph because it's done pretty well. But where do you think these people are closest together? I'm pretty confident that this distance has to be closer than these two. Just kidding, these two. 100% because I know that Phil and Olivia are closer together at that first one. Now, here's the algebra part that's just kind of interjected within without having talked about everything else. Could we find equations of these lines? Okay. Which one do you want me to do and which two do you want to do? Let's do one together and then we'll divvy up the labor after that. Okay. Together as a class, Olivia, Phil, or Nat? Whose equation are we going to come up with? Phil. Okay. Follow-up question. You may or may not know the answer. Why do I need to know their equations? So the slope is going to be valuable. The slope I think we already have. Beyond that, though, if I could see exactly when these two meet here, we've already identified the time. So our goal is to try to find where these two equations cross each other. Algebra muscles, flex them. Algebra language, flex it. How do you find this point where these two lines meet without just eyeballing it? Set them equal. We're just solving a system of equations, and to do that, we need the equations. So, realistically, I don't even care about Phil. He don't matter to me right now. Let's check it. If this is the closest place, that's the only two that we need. That's where which colors intersect? Green and yellow, or Nat and Olivia. Whenever they're at the same spot, that's our shortest distance. So I'll help us do Natalie's equation. So I'm going to use y sub n, representing an equation y sub n. Who's green? Boom. Y sub nat, if I just don't want to write the whole thing. So we're going to find this equation real quick. Now the good news is that these are straight lines, and I guess lines just in general. To find the equation of a line, what do we need? So possibly an intercept, but we definitely need a slope, right? Because you either need slope-intercept or you need point-slope. Either one of those are going to work. So let's check it out. Do you know the slope, which I'm going to indicate m sub n for Nat? Do you know the slope of the line that we drew for Nat? Let me rephrase that. I'll tell you, you know the slope of the line. What is the slope of Nat's line? How did we draw that green line? It's 40.25. It's just her speed, okay? 40.25. Do you know the y-intercept of that green line? Bless you. Not directly, but I think we can reason it out. We could pick this point up here and say this is 40.25 over a change of 1/2, or check this out. If, and we didn't do it, but if I let Nat's line keep going, I could probably work it out, don't you think? How far in time would I have had to go to get back to the y-intercept, or the y-axis? You'd have to go, careful, time. Half an hour. Do you know how fast Nat goes, or how far she goes in half an hour? So that's a full hour. What's half of this number? 20.125. Is that what she said? I'm so sorry, I misheard you. Okay. Could we have used point slope and done the y minus y1 equals m x minus x1 and plugged it in and got the same answer? This is more efficient, it's faster, because I can do half of 40.25. Okay, fine for me, I'll give you a second. What other equation do we need? Olivia, so I'm going to call this y sub what? Y sub O, which I kind of hate. So I'm just going to do y sub OL, because sub 0 is a pretty common usage. Okay, equation. I'm going to give you guys a second. Find me Olivia's equation. I'm going to be walking around to get my steps and make myself available if you have questions or your neighbor isn't answering something like clearly. So y equals mx plus b is what I heard. If you want to write this, that's fine. But I think we have all the information to just plug it in. Y equals... I forgot an x over here just for the record. I'm not going to use x, I'm going to use t plus 20. Now, same thing, in case you didn't catch the comment I made. This is negative 40.25 times the amount of time t. I forgot this t when I wrote this initially. It's just like x, we're just using t, bless you. Okay. Last little thing. If I'm trying to find, I now have their equations and I can see them. I want to find this point. It's where those two equations have the same y value, right? Or the same x value, doesn't matter. These are both solved for y. And oh my gosh, I'm going all over the place just notationally how this is looking. This should be y sub n in the end because I did it in 2 steps over there. So I'm going to make some changes. Can I get your eyes on the board for a second just so you can see? This slope, we wrote it and then we just finished off the equation. This should be y sub n now that we've worked that out. I just didn't split it into 2 lines here. I did here, not here. Okay. So check it out. I need you guys to solve for me when their y values are equal. So using your calculator or your mind, I want you to set these 2 equations equal. 40.25t minus 20.125. And that's going to be exactly equal to what equation? Good. Set them bad boys equal, solve for t. I'm going to give you guys a head start. I will show the work instead of just using ellipses, but I'll give you a moment. Approximately. Is it 0.71? 0.71, and there's probably some more decimals, but I'm okay with that. Okay. For this problem, we have just decided that this value, and on my graph, because I was careful with it, I'm using a straight edge, I believe it. If I'd got a number that said like 1.8, I'd look at it and go, whoa, either my graph is absolutely awful or my math is absolutely awful, or both. Okay. The actual question says, at what time? We found that like 0.71 isn't a time, is it? So with your group, I want you to determine what time this is. 0.71 is t. It's not 11:30.71 though. That doesn't make sense. Talk it out with your neighbors. Let's see if we can make sense in context. When I write this t equals 0.71, last little part, I won't count you wrong in a problem, but this is going to lead to mistakes. 0.71 what? How do we measure time? Hours right now. Okay, now that doesn't mean anything because do you know off the top of your head 0.71 hours how long that is? Now, it's not 71 minutes, which is a pretty natural mistake that people make, but we know that there's not 100 minutes in an hour, so that's hopefully easy to fix. How would you figure out how many minutes that is? 0.71 of how many minutes? 60. So 0.71 of 60 pushed me to like 43 minutes. 42.6 something. Why did I change it to 43? Sig figs. Because I see that I have 2 within all of these equations. Okay. Now, looking at that, does that still answer the question? At 43 minutes. So, there's not many times that I want you to like write, but contextual answers, I need them. At 12:13, they, implying we're talking about these exercise enthusiasts, are closest. Now, I'm not going to put a period on the end of that sentence yet because there's another question. What's the second question? So that's a weird way to word it as well. When I ask you what length is the distance interval, what is that even asking? Yeah, so there's a bunch of ways that you could answer this question. Eyeballing it, can you guys tell me exactly where that is? How many kilometers north we are? You can give me a ballpark. If only we could work that out, because we just found that this was the ordered pair 0.71. How on earth would you get the distance out of it? To what? Which equation? Either yellow Olivia or green Nat. And I think you knew it, Ruff. I just want to be real specific with it. Okay. Now, I don't care whose equation you plug into. We found both of them. This side of the room, use the green equation, Nat's, and plug in 0.71. You guys use Olivia's and plug in 0.71. And we should get the Y value for this ordered pair. Shout it out once you have it. 8.45? Okay, so I'll call it 8.5. Can I get a second? Third? Okay. So now that we have that number, they are closest. At 1213, they are closest. And what is that distance? And there's a few ways you can word this. Could you find the actual distance between them? You could. However, I think that we have enough to answer this at what distance, because it's really unclear. If I claim 3 different answers, could I say 8.5 north of Waterfall? That's literally the value that we just found. 8.5 kilometers north, rather. So let me make that kilometers. Is there another way you could have given me that answer? You could have also said 11.5 kilometers south of what? South of the dock. Is there another way that you could answer that question correctly? Because the two distances we found have been this far north or this far south. Is there a third way you could answer it? Would it be possible to find exactly, oh, this color's going to be awful, exactly this distance? So I'm going to be real, I'm going to call somebody out. Abigail, you did a problem in pre-calc similar to this. How would you find just this height or this distance? Could we just do y of fill at that time, 0.71 minus 8.5, since we already know that number? And we could get the same distance. In reality, I prefer the first one because it's the first answer that we arrive at, and it's a pretty natural way to talk about location. But any one of those would be fine. I don't know the actual distance, just a heads up. You want to find it? Okay, cool. So we spent more time on that than I was expecting. That problem, I wouldn't say is exceptionally hard in the realm of physics. Setting it up is wonky because the problem's so ugly and worded funny. Mathematically is where, if you struggle, that's where that problem is most likely going to make you struggle. Everything linear equations that you've seen in Algebra 1, Algebra 2, or pre-calc is going to show up, just so you guys know. We won't do much log stuff, which is nice. I want you to get a little bit of practice with these. So I have two. Question? Just clearing. Okay. Let's check it out then. You want it to be mathier or conceptualier? Mathier. Okay, tonight, starting right meow, you get the privilege of homework 2.3. And this one's weird. You're going to find it on page 42. It's not really weird, but it's not the end of the section. We'll do the discussion on those tomorrow. I want you guys to do 11 through 15. Cool. Homework 2.3, page 42, 11 through 15.